So starting section 13.1 with integration, and the idea in this section is that integration is just the opposite of differentiation. Now we find out later in the chapter that's a slight fib and there's a little bit more to it, but basically that's the way that we're going to do these questions anyway, so it's a good way of thinking about integration. So it really is sort of this straightforward, that when we are differentiating, we take a function, let's say y equals 3x to the power of 5, and what do we do? Well, to find the derivative, we would reduce that power by 1, so it would be x to the power of 4, and we bring the old power down to the front and times, so we'd have 3 times 5 is 15. So that was differentiating. If I'm asked to integrate, so I'm told dy by dx, and let's say it is 2x to the power of 3. Well, let's do the opposite of everything we just did. What could the function be? Well, if I increase the power by 1, I'd get x to the power of 4. And then if I divide by 4, I'm going to get 2 divided by 4, which is a half out the front. Okay. Now if we check that, take this and differentiate it, bring the 4 down to the front and times, that's 4 divided by 2, that gives us this 2, and reduce the power by 1, that gives us the 3. Okay. So it's useful to have in your head a little sort of sentence that you say to yourself, like increase the power by 1, divide by the new power. In the same way that when we were differentiating, we say reduce the power by 1 and times by the old power. Here we're increasing the power by 1 and divide by the new power. Okay. Now that's not quite enough to get us through exercise 13a, because we've got a slight problem here. Let's take this example, 2x cubed. And we say, well, if that was the derivative, if that was the gradient function, then the function must have been a half x to the power of 4. Except, if you differentiate a half x to the power of 4, you get 2x cubed. But if I differentiate a half x to the power of 4 plus 6, if I differentiate that, I also get 2x cubed. Because half x to the power of 4 differentiates to 2x cubed, and the 6 vanishes. Because if you differentiate a constant, you get 0. If I differentiate a half x to the power of 4 minus 17, I also get 2x cubed. So when I take 2x cubed and I integrate it, what I get is a half x to the power of 4 plus a constant. There might be a constant there. So the way that we do this, and I'll take the first example from the first exercise, the first example, first part of the first example. They'll ask us questions in this exercise that look like this. The derivative of a function is x to the power of 4. What was the function? And we'd say, well, that function y would have been increase the power by 1, divide by the new power, plus a constant. And don't forget the constant. Okay? So every time you integrate, you've just got to stick a constant down after it. It's really easy to forget in exams, so just watch out. Somehow try and get that one in your head. Everybody at some point has been in a test and has forgotten to add a constant of integration, has lost a mark and has kicked themselves for it, and if you're lucky that'll happen before the actual exam, and then you'll remember in the real exam. I'll do one quick last example because that really is it in this section. dy by dx, so this is example 3. So I can have something that looks like this. Well, increase the power by 1, that's x squared, divide by the new power, that's 3. Increase the power by 1, that's minus 2. Divide by the new power is minus 1. Increase that power by 1, that's x to the power of 1 and a half, so 3 over 2. 3 divided by 3 over 2 is going to be 2. Okay? And then I don't need to write the 1 in there, do I? So we can just integrate term by term the same as we did for differentiation. You've got to be careful, actually, I've made a mistake here. dy by dx is that, I can't just put equal to this, I need to put y is equal to this, because otherwise I'm saying dy by dx is equal to this, which is equal to this, and these two things aren't equal. So you need to make the difference clear in your notation. You'll see in the exercise that obviously they'll start off, as we did with the differentiation chapter, you'll end up with expressions here that aren't in this nice form. So if you end up trying to integrate something like x square root of x, you need to rewrite that as x to the power of a half, and now you can integrate it. Okay, so it needs to look like something times x to the power of something if we're going to be able to integrate or differentiate it on these chapters 12 and 13. Now, if I'd been clever, I'd have done this on purpose. but I've just realised I finished this example and I forgot the constant of integration, didn't I? So there's my integral. I need to put a plus c on the end. So I've just warned you not to miss out your constant of integration and how easy it is, and there's me doing it immediately straight away. So integrate, that gives me these three terms. Don't forget to add your constant of integration.